Hi guys, this is Ms. Miner, and this is Unit 3. We're starting with homework A, and our goal today is to be able to understand and interpret a qualitative graph. That's a mathy way of saying we just want to understand what a graph is telling us. If we're given a graph, can we read it and determine what it's telling us, right? So the first thing that we want to do, I'm actually going to go back here and I'm going to add a page in here because I want to do a little bit of review from 7th grade, graphing, right? And the first thing that we need to remember is that I have these two axes and it creates what's called the coordinate plane. Coordinate plane. And the coordinate plane is just a graph, right, where I have an x-axis and I have a y-axis. And the x-axis is just like a regular number line. And we start with a 0 right here in the middle. That's where x is 0. And then I have all of these little numbers coming out from here. And all my positive numbers go to the right. So I'm getting more and more positive in this direction. And all my negative numbers go to the left. And so I'm getting more and more negative moving out in that direction. My y-axis is kind of like a thermometer where I have 0 in the middle. So this spot in the middle is 0 for my y. And then all my positive numbers go up. So I'm getting more and more positive up. And then my negative numbers are on the bottom and go down in this direction. So that's kind of my coordinate plane. And we started using that when we were in 7th grade. And we said that each of these sections was called a quadrant. So we have 4 quadrants. 1, 2, 3, and 4. And these are called quadrants. It's quadrant because there's 4, right? So quad means 4. And we have 4 parts to this graph. So let's start there. That's kind of what we started with when we were graphing. And today we're just going to be focused on this quadrant, the first quadrant up here, where x is positive and y is positive, because normally in the real world we have graphs that look like this, and all of our x values are positive. So again, here's my x-axis, and here's my y-axis, going up and down, and then each of these lines would be like my values for x. So if this were 0, then this would be 1, 2, 3, 4, 5, 6 units, like a measuring tape or a number line. And those units just depend on whatever I'm graphing. My units for my y value would be 0, 1, 2, 3, 4, 5 of whatever I'm graphing. And we learned that the x value and the y value, if I want to put a point on my graph, I use what's called an ordered pair. And it's the coordinates for a point on a graph. So if I had the ordered pair 0, 0, I would put my dot right here at what's called the origin. The origin is the spot where x is 0 and y is 0. And this is written like this as an ordered pair because my x value and my y value are in order, like alphabetical order, x and y. Any other point on the graph can be written as an ordered pair. If I want to go where x value is 2 and y value is 4, here's my x value first and my y value second because they're in order. They're an ordered pair. And the way that I graph it is I kind of go along the x-axis until I get to the line that represents the 2, and then I follow that line up until I get to the line that represents the 4 on my y-axis. And we call these good points. I call them good points. A lot of times we say they're good points in math because they're represented by whole numbers, right? Anywhere where these two lines meet up, I have a really what we call a good point right here, because it's where x is a whole number and y is a whole number. So anytime I have kind of these little sections where my x value and my y values meet up, that would be where x would be a whole number and y would be a whole number, and we call those good points because they're easily identifiable. And if I have a point that's in the middle, right, that would be some sort of fraction number. This would be like saying 5.5 in my y value, and sometimes that's just an estimated value, and so, or an estimated place on my graph, and so that's a lot harder to be accurate if I'm not talking about a whole numbered point. Well, that's important when we start graphing things later on, is knowing where these really good points on the graph are located. And it's wherever I have an intersection in the lines between x and y. All right, so when I'm going to graph an ordered pair, let's put another ordered pair up here. Oh, sorry. Let's graph the point 3, 4. This is where x is 3 and y is 4, so I go to where x is 3, and I follow it up to where y is 4, and I put a point there. Now, you don't need to have these lines on there when you do it. I put those lines on there because I'm just trying to illustrate exactly where that point is, where x is 3 and y is 4. I just want you to see exactly where my eyes are looking at, so I'm just trying to illustrate that for you. And those are called ordered pairs. Another synonym for an ordered pair would be a coordinate pair. And that's the same thing. This is the same thing as this. It's just another way to say it. You might hear me use both of those things because it is the coordinates of where it's located on the graph. Okay. So when I'm graphing, there's a couple of things that I always look for on the graph. And the first thing that I always look for is the graph scale. So let me write that word on here. That's another really good vocabulary word. I look for the scale. And the scale are these numbers down here, and they're going to tell me what my data, what kind of data I have, right? If I have really big data, I might have a different scale there. And so I might not be counting by ones in my scale. I might be counting by, let's say, 2s or 5s or something like that, where each one of these lines represents a larger amount, right? If I had really big data, I might want to count by 5s instead of by 10s, because then I could graph more data on here. I could graph larger numbered data on here. So I always want to check for scale, and when I create a scale, I want to make sure that I'm creating a scale that fits my data. I wouldn't want to count by 10s on my scale if I had data that was represented in numbers that were like in ones, like 1, 2, 3, 4, 5. I kind of want my scale to fit the data that I'm graphing. I also need to know that my x-axis does not have to be scaled the same as my y-axis. It just depends on the data for each of those variables. If my data for my x is in big numbers, I might scale my x value by 5s or 10s, and then if my y value were in smaller amounts, I might scale my y-axis by 1s or 2s or something like that. But I do have to scale it in order, so that if I decide I'm going to count by 5s, then my scale has to be the same. So I have to count every box over here the same amount. So from here to here, it would be 5 and then 5 more and then 5 more and then 5 more, so that each line or each box on this graph represents the same amount. So when I scale it, I have to count by a certain value so that all of my boxes or lines on my number line, right, are the same amount of value. So if I were going to do by 5s, then each line on my graph would have to represent 5 more. So I want to make sure that they are equal in value between there and then again between here and here, right? So that those two amounts were the same value. And that would go the same thing for my y-axis. If I were going to scale my y-axis, I'd want to make sure that it represented the same amount of value between this line and this line, and then between that line, and so forth, so on and so forth. So if I decided, okay, I want to scale my x values by 2s, then that would be 2, 4, 6, and 8, like that. So that's how scale works there. Okay. The next thing that I always want to look for on my graph is the labels. And when I create a graph or when I'm using a graph to help me read data, I want to always look for my labels. I want to know what is being graphed on each of these axes. So each axis will have a label. If I'm talking about feet per second, then my time in seconds, I would have to make sure that I'm labeling what my x-axis is. And then over here, this would be like my distance or my length in feet, right? And I always want to make sure that I'm labeling my axes so that when I'm reading my graph or when someone else reads my graph, I know exactly what I'm talking about and what has been graphed on that graph. So labels are really important to read. And just so that you're aware, x is the independent variable, right? We already kind of talked about that. And 99.9% of the time, if I have some sort of time measurement, like months, years, days, hours, seconds, anything like that, it's going to be graphed on my x-axis. And the reason why is time is very, very, very independent. We don't have control over the time that is going by. And so time is not really, almost never, our dependent variable. Remember, the y was the dependent variable. So an important piece of information is that if you have time that you're graphing, it's most often going to be graphed on your x-axis because your x variable represents your independent variable. Okay, so that's a lot of really good vocabulary and a lot of really good thoughts about graphs. Let's go ahead and just try and read a graph or come up with a scenario for a graph. So what I want you to do right now is go ahead and pause this video and take a look at this graph that's here on the left-hand side and see if you can come up with some kind of scenario or story in your mind that could possibly create a graph like this. So what would make a graph go up and then down and then up and then down like that? So try and create a scenario in your mind that might create a graph that looks like this. Like if you were reading this graph, what could you come up with in your mind? So pause the video and just try and brainstorm some ideas. And then in a minute, turn your video back on and we'll give some ideas and talk about what could possibly create a graph that looks like this. And you can see if your ideas match up with my ideas. Okay. So I hope that you did that. I hope you paused and you just brainstormed some ideas. But the first thing, whenever I'm trying to come up with something, what I like to do is I like to think, okay, well, what kinds of things do we graph in the real world, right? What goes up and then down? Well, a lot of times when things are going up and down, right, then we're talking about height. So maybe this is height over time, right? And then maybe something that goes up or down in the real world would be an airplane, right? And so maybe this is a graph of an airplane taking off and landing at different airports or something. Maybe I had an airplane take off. It flew up to a height of 10,000 feet, and then it started its descent down into a new airport. It landed in the airport, then it took off again from the airport, picked up some passengers or whatever, and then flew just to not as high of a height as it did the last time. Maybe this time it only went up to 5,000 feet or something like that, then landed again and then took off again, right? And so maybe this is height versus time, and then landed again at an airport. So that could be a situation where I created a graph, or a graph came but we also have other kinds of graphs that go up. Maybe I was talking about distance, right, versus time. So now I'm talking about something else that happened. This could be something where maybe I got in my car, right, and I was just driving kids home. And here's my house. I started at my house, right? And then I got far away from my house, and then I dropped a kid off. I turned around. I started coming back towards my house. I stopped at my house. I got my daughter. Then maybe we had to go to her soccer practice, so we were some distance away. We turned around. We got back home, and then we got back in the car and drove again, right, to pick a daughter up or whatever. I have daughters, so, and then I drove back home. So maybe this was a graph of distance versus time. So these are just ideas to help you kind of start to figure out scenarios for different kinds of graphs. So now I'm going to give you a scenario, and I want you to sketch a graph that might represent this scenario. So label your graph. Start by labeling. That usually helps us kind of think through, or helps us kind of, at least for me, I usually start by saying, okay, what is it that I want to graph here on this graph? And then read the scenario and see if you can graph it. So pause the video and see if you can graph the scenario. Let's read through it together. A dog is sound asleep when she hears the doorbell ring. She quickly runs to the door and stares out the door. As the visitor walks away, the dog slowly walks from window to window, searching for whoever rang the bell. She eventually gives up and lays back down and goes to sleep. So try and come up with a graph that might represent that scenario. Pause the video now. Okay, so I hope you paused the video and thought up a scenario that might, or a graph that might represent the scenario, and you can kind of see if yours matches mine, or if you still, after we kind of talk through it, maybe you'll change your mind and decide, oh, maybe my graph doesn't make sense, or make some changes to it in order to help you kind of start figuring out how graphs are created. So we're not going to be super accurate on this, right? But we are just going to kind of get an idea of what this graph might look like. So first, let's graph time, right? And then let's graph, let's start by graphing distance from her dog bed, right? So what happens when she's laying on her dog bed? Well, she's 0 distance away. So for a short period of time, she was asleep on her dog bed, and then she heard the doorbell ring. And so what does she do? She runs really quickly. So I have kind of a steep, quickly running away distance, right, to the door. The door, I would assume, is some distance away. And so I have a kind of a steep line going a quick distance away to the door. And then she runs to the door and stares out the door, right? So is her distance changing when she stares out the door? No, her distance is staying the same when she's staring out the door. And as the visitor walks away, the dog slowly walks from window to window. Well, she's still some distance away, right? Maybe she's getting closer to her dog bed, right? Very slowly getting closer to her dog bed as she walks towards the window. So maybe her distance is like kind of going down, or maybe the windows are at the same distance. I know for me, my windows are at the same distance as my door. I have a couple of windows that are kind of next to my door. And so maybe she's staying at the same distance as she walks from window to window, searching for whoever rang the doorbell. And then finally she gives up, and maybe she kind of just slowly walks back to her bed, and then eventually she gets to her bed and goes back to sleep, right? And so my graph for my distance over time is something like this, right? Where she ran out to the door, then kind of stayed away from her dog bed, and then slowly came back to her dog bed and laid back down again. Now, if you didn't do distance and time, right, your graph might look different. So let's try something different now, and let's see what a different scenario might be for the same situation, right? So what if I do time, but this time instead of doing distance, I do speed, right? Let's graph speed this time. So she's laying down, right? She's not going any amount of speed for a certain amount of time, right? But then when the doorbell rings, she quickly runs to the door. So then my speed is really, really steep, right? Because she quickly runs to the door. She goes very fast. And maybe she's getting faster and faster and faster as she gets to the door. And then what happens when she gets to the door? Stops, right? So immediately, sorry, I want to make this even better. She gets here and then immediately stops because she's at the door, right? And so her speed is not going anywhere anymore. It's immediately back down to 0. And then it says she slowly walks from window to window. So she might be slowly increasing speed, and then maybe she just kind of slowly levels out when she gets to a certain kind of slow walk, and from window to window. And then eventually she gives up and lays back down, and so her speed kind of like slows back down to a stop and then stays there, right? So maybe my my graph for speed versus time looks very different than my graph of distance versus time, and it will depend on what I decide I'm graphing here, right? So different graphs depending on that's why labeling can be very, very important, because labeling could determine the shape of my graph just by what I decide I'm graphing here. Okay. Yeah, I think we can move forward. Okay, so what I want you to do right now is label your graph and decide what has been graphed here. Here's a little dude, right? And then write a scenario that might fit this graph. So again, go ahead and pause the video and decide what you're going to label your graph, and then come up with some kind of scenario. Tell yourself or write it down what could have possibly have created the shape of this graph. Okay, so I hope you paused the video, and I'm just going to give you one scenario here, right? Well, maybe a couple, but let's do time again, and let's do distance. If this is my graph of time and distance, well, right here I slowly kind of got farther and farther away from wherever I was. So maybe he was at home, right? Maybe he was at home, and he just kind of slowly walked away down the neighborhood. Oh, sorry. To a certain point, and then he decided to turn around and come back home. So he turned around, and this is a little bit steeper on this side, so he's going a little bit faster. So maybe he just was walking here, right? And then maybe here he jogged home. And then he was at home for a little bit of time. Let me just change color here so we can see where I'm highlighting on that red line. He was home. Oh, sorry. He was home for a short amount of time. There was no distance away, right? And then here's this line that's going very, very fast up here. So maybe while he was home, he got into a car, right, and drove away fast, because that's going very, very steeply a far distance away. So I'm not talking about speed here. Even though this line is a little bit flatter, that's what's telling me, because it took him a lot more time, to go this distance, right, than to get this distance away, right? There was a lot more time in between this interval here and here than in between this interval here and here. And because of that, I can see that he was going a little bit slower here, just because of the time that it took to get that distance away. So even though I'm graphing distance, I can tell a couple of things about this graph just based on the scenario. And remember, I just came up with this, right? I said I'm going to graph time and I'm going to graph distance. Oh, well, there we go. And so that kind of determined what information my graph was giving me. If I were going to graph something else, and maybe this is something that you might want to try on your own, is graph something else, graph time versus speed, and then see what information you could get from that graph. Okay, the last little bit, we're just going to do a matching activity on our homework. So I wanted to kind of give you some tips for when you're trying to match a graph to a word problem or a word scenario. So we're going to use these 3 scenarios over here, 2A and 2C and 2F here, just to kind of match them to some graphs, okay? And what I like to do is I like to start with the word problem and then see if I can match the graph to the word problem. Sometimes I find that helps me kind of figure out the graph. And I use a process of elimination in order to do it. So this scenario says that the graph shows the cost of hiring an electrician per hour, including a fixed fee. And so remember, this is kind of like our y equals blank, x plus blank. And when we were looking at these, when we were writing these, now we're going to try and kind of come up with some graphs. And one thing that sticks out in my mind is that this is a fixed fee, right? He has to pay that up front. So the starting place of my graph, the initial value of my graph, is not going to be 0. I know that because he has to pay some money right up front before any work happens. And so in my mind, I'm kind of looking at these graphs and I'm saying, oh, look, this graph starts at 0. And so I know it's not going to be that one. This graph starts at 0. So I know it's not going to be that one. This graph starts way, way, way up high and comes down. That's kind of what this graph is telling me. And so I know it's not going to be that one. So in my mind, I can already start to eliminate some of the graphs that don't fit scenario 2A. And then I also know that the cost of hiring an electrician is per hour. So as time goes by, right, then my cost is going to go up. And in my mind, I can already kind of see the graph like going up from there. So I know this graph can't start at 0 and that it has to go up. So I know that it's not this graph, and I've already eliminated some of these things, right? So now I'm unsure. It could be 2-5. It could be 2-6. And so I want to kind of see if any of these other scenarios might fit those graphs, right? And if I read down through some of the other scenarios, I see that right here in 2F, it says that the population started out slowly at first, but then increased more quickly. And so I can see that this one kind of starts out slow and then goes up. And so this one is probably 2F, and this one is probably 2A. So I kind of use a process of elimination on these, and I read through my scenarios first so I kind of know what I'm looking for. And I start to try and imagine in my mind what I think the graph is going to look like, and then I use process of elimination to get rid of them. So I kind of know, I think this one is 2F and this one is 2A. I think I've got those right. And then for 2C, I'd go back through again and I'd say, okay, for 2C, it says the graph shows speed against time for a car traveling at a constant speed. And so what do I know about the word constant? Well, constant tells me something very important, right? Is it increasing? Is it decreasing? In this one, it's none of those things, right? So I know it can't be increasing or decreasing. So the only one that is constant here is 2-3. Okay, so that's kind of how I do that. I use this process of elimination in order to decide which graph matches. And you can do that on your homework today. Try and read through those scenarios and then use that to help you solve your equations, or figure out your graph that matches. Oh, excuse me. Okay, well, that's all for 3A today, and good luck on your assignment. Please remember to email me or Mrs. Zeider, or join us for our Google Meet if you need some additional help.